Software Engineering Radio Episode 68, Garbage Collection and Transactional Memory with Dan Grossman. Hello listeners, welcome to another episode of Software Engineering Radio. In this episode we are going to talk to Dan Grossman about transactional memory and garbage collection, about an analogy between the two topics. So Dan, welcome.
Thank you.
So Dan, before we actually dig into the topic, why don't you introduce yourself to our listeners?
Sure. I'm Dan Grossman. I'm a faculty member at the University of Washington in Seattle, and I joined the faculty here about 4 years ago after finishing my PhD at Cornell University. Before that, I was a university student at Rice University in Texas, and my background has always been in programming languages, particularly safe languages, languages for increasing robustness and software quality. I used to work more on low-level languages, C-like languages, where you want to implement an operating system or low-level sort of systems code. And more recently, I've become very interested in concurrency and trying to make programming easier for multi-core architectures and sort of the mass parallel programming that we're told is on the horizon.
Okay, and at this year's OOPSLA, you have got a paper about transactional memory and garbage collection. So most people, I think, know what garbage collection is, but can you give us a brief introduction about what transactional memory is all about and what it's used for?
Sure. Transactional memory is the idea that your memory operations, you know, a memory is just things you can read from locations and write to locations. And typically, if you're down in assembly language or even up in a language like Java, you do individual reads and writes, and as soon as you do them, anything that's happening concurrently, another thread or whatever, could see those. There's only sort of one memory, and it works at the granularity of individual reads and writes. With transactional memory, you just have the ability to group a collection of reads and writes into a transaction, very much like you can group a bunch of database operations into a transaction in the database setting with persistent storage. But now we're really dealing with program state, with volatile memory, and you can group them together. And by grouping them together, you guarantee that either all of them happen or none of them happen, and that any concurrent observer sees all of the updates at the same time.
So actually, just to connect this to a previous episode on SE Radio, we talked with Brian Goetz and David Holmes about concurrency, about advanced concurrency, and right at the end they mentioned transactional memory as something that's on the horizon that might revolutionize concurrent programming. So can you provide us an example of how we would use transactional memory if it were available? And of course, it's always a bit of a problem to talk about source code in an audio-only form, but let's try.
I was thinking the same thing. I thought, how will I ever do this without waving my hand?
Well, line by line.
We'll give it a try. So the simplest way to think about it from a programming perspective is that it gives you a synchronization mechanism that you didn't have before. Right now, if you program in Java, the most common synchronization mechanism is locking, using synchronized statements. Okay? And the reason why you use a synchronized statement is because you want the things in that statement to all occur, while no other thread has that lock. And here we're getting an even stronger guarantee. We're saying let's get locks completely out of the picture. And you say the same thing. You say atomic left curly brace, and then some statement, and then right curly brace. So instead of saying synchronize and a lock to acquire, you just say atomic. It's just a keyword, and you don't specify any lock at all. And that just says that the computation that happens in this block has to appear to happen all at once to any other thread.
And again, to connect to the other episode, in some sense, it's basically moving something that has been provided in the form of libraries and which had to be obeyed as a protocol, moving that into a language and making it more declarative. And by doing that, of course, the compiler and the runtime system has more options to optimize, right?
That's exactly right, in the sense that when you have an atomic block, you're not specifying any sort of particular locking protocol or anything like that. You're just saying this has to happen all at once. Now, absolutely, the role of the compiler in the runtime system now is to preserve the illusion of it happening all at once.
Yep.
And what it really tries to do is preserve as much parallelism as it can.
Yep.
And the way it basically does that, there's people who, very, very smart researchers who've devoted years to the details, but the basic idea is that you have these different atomic blocks or transactions running at the same time, and you just do enough bookkeeping to make sure that they're accessing disjoint memory.
Mm-hmm. Yeah.
And as long as they're accessing disjoint memory, it's fine to let them happen at the same time. The programmer can't tell that they happen at the same time.
Yeah. Okay, so your claim in the paper is that transactional memory is to shared memory concurrency as garbage collection is to memory management. So before we look at the analogy, and actually when I read the paper, I was quite intrigued. This is really cool stuff. I mean, it's really interesting how you wrote the paper. And so let's first reintroduce a little bit about garbage collection, how it works, and things like the basic idea, the different algorithms, so we can connect to that when we talk about transactional memory later.
I think that's a great idea. And maybe something else I could say even before that is that this is an essay, which is a slightly different kind of paper at OOPSLA. So there aren't, nothing we'll talk about or nothing in the paper is necessarily a new technical result.
Sure. Yeah.
It's really a new perspective. This analogy is not something that's been focused on before or even said before. So this is really a reorganization of existing knowledge.
Yep.
So to do that, you really have to start from the beginning, and you have to give a perspective on, what is garbage collection. And, you can sort of take the view of, oh, well, it's that feature that means you never have to write freeze, and you don't have any space leaks, and you don't have any dangling pointer dereferences. But if you take a step back, that's all true. But really what garbage collection is a language mechanism by which the runtime system can reuse space in a way that the programmer can never tell. From a language definition perspective, in a language like Java, all you do is allocate new objects, and they live forever. And it's up to the garbage collector to maintain that illusion while actually reusing memory. And the key approximation that it uses, and I think it's important to realize it's an approximation, is this idea of reachability. Okay, the way garbage collectors work from 35,000 feet is it looks at all the variables you're still using in your program, everything on your call stack and all your global variables, your static fields, and it sees what objects those point to, and then what objects the fields of those objects point to, and so on transitively. And it keeps all of that, and it collects everything else, which it calls the garbage. And the reason why I call it an approximation is this can lead to keeping objects around longer than necessary.
Right.
And so, for example, if you put a very large data structure in a global variable and never use the global variable again, you're just wasting space, and there's nothing that garbage collectors can do about it.
So, and based on that basic idea and concept of reachability, there are probably a couple of different higher level algorithms and probably a couple of tricks that you can use to optimize these kinds of things, right?
Right. At 35,000 feet, I just said it finds everything that's reachable. If you go down one level deeper, you say, well, how does it do that? And one approach, which is called tracing garbage collection, and that's an approach that subsumes some phrases or some ideas that listeners might have heard, like copying garbage collection or mark sweep, is to have the garbage collector literally go through memory, marking everything that it finds that it's alive. And another approach is to basically use automated reference counting. So in automated reference counting, as the program is running, the system just keeps track of how many references there are to each object. And when you reach 0, you can go ahead and collect the object because you know that it's no longer reachable.
Yep. There is also real-time garbage collection. That's probably a very special case for embedded systems, right?
That's right. So this phase, if you will, of finding what's reachable is something that's not under programmer control. In a language like Java, it could happen at any moment. And if it takes a long time, that could mess up any sort of application that has timing needs. That either soft timing needs, like you need an interactive application, or hard timing needs, like you need to respond to sensors and signals like embedded systems have. And so taking a basic garbage collector and giving it the property that it never stops the regular program for more than a very small amount of time is something that's been studied. We have algorithms to do it, but it's significantly more difficult than a basic garbage collector.
Okay. So now that we talked about GC, garbage collection, as an introduction, let's now look at an introduction to concurrency and transactional memory.
Sure. So what I did in this analogy is really assume from the beginning shared memory concurrency. So people who are more familiar with message passing or coordination languages, there's a lot of models of parallel programming.
Erlang is becoming quite hyped these days with its actor-based pure message passing thing.
Absolutely. And I'm actually a pretty big fan of things like message passing languages. But that's a topic for another day.
Yeah.
So, for today, I'm really imagining really the parallelism model we have in modern object-oriented languages like Java, which is you have multiple threads. A thread can create a new thread. These are separate bits of control. You might have multiple running at the same time, or you might be time slicing running one for a little while and then running another. And the way they communicate, because it's multi-threaded programming is not interesting until the threads communicate, is one thread writes some data to a location and another thread reads that location. And that's exactly what we mean by shared memory. And then the next step is, well, how do they coordinate, right? How does one thread know that the value has been written? How does another thread, how do you keep two threads from writing to the same location at the same time? And to me, in general, that's what you have synchronization mechanisms for. And it's all the things one learns about typically in an undergraduate operating systems course. Locks, monitors, semaphores, all of those things. And you need something like that, and it's a classic result of parallel computing that given one, you can typically code up all the others. But you need something to, the way I like to think of it is restrict the interleavings of different threads.
Right.
You need to make sure that if one thread is stopped at a particular point right between two statements, and that can happen, that another thread won't proceed to read the partial results of some computation that isn't finished yet.
And of course, then we have all these problems resulting from that about deadlocks and live logs. If you try something forever, or if you try to acquire a log that's already acquired and never released and stuff. So that's the typical problems you get from implementing concurrency as a protocol without language support.
That's a great point, and we should definitely walk through those problems, is you have things like deadlock, which is a collection of threads unable to make progress because they're all waiting for something else to do something before they continue.
Yes.
And in some sense, what you've done there is you've taken away too many possible thread interleavings. The programmer has through a programmer error. But if you get rid of too many locks, then you have some interleavings you didn't want, and those are typically what we call race conditions. And this is exactly the tightrope that programmers have to walk when they're programming with locks. Is if you do too little locking, you'll have race conditions, and if you do too much, you'll have deadlock.
Okay, so we talked about before how transactional memory simplifies these things by making things more declarative and giving the runtime system, well, let's say the right level of freedom to optimize what's optimizable. So is transactional memory a software-only thing, or is it actually a software-hardware combination?
Yes, and all the more. So transactional memory has been very, very active as a research topic in the last 2 or 3 years, both from the computer architecture community and the parallel programming, parallel algorithms community, and also the programming languages community. And we're having joint workshops, and we're all talking together, and there's just been a lot of work. And to answer your question more directly, there's been several different proposals on how to provide transactional memory completely in hardware. So you can really imagine down at the assembly language having new instructions like begin transaction end transaction, and abort transaction.
Yep.
So the idea is that after you say begin, any loads and stores you do, you'll be allowed to say abort, and then it's as if none of them happened. Or you can say end transaction, or sometimes called commit transaction, and then they all become available to other threads. What's particularly good in hardware is that they can do conflict detection. They can do this runtime optimization of letting things happen in parallel if they can, very effectively using ideas similar to cache coherence protocols, which we've known how to do for many years. What they can't do as well, and I don't mean to criticize because there's been very good research papers on how to do it, is long transactions that access more than just a few memory locations. And their software implementations, things done entirely with existing instruction sets, but just through compiler techniques, tend to do a little bit better. They also tend to be slower. Typically when you can do something in hardware, you do. But software is also more flexible. We can explore different algorithms and incorporate new advancements much more quickly. And there's been important work on hybrid systems. And I think that many people believe that that's where the production quality systems will end up, is that you will use hardware to try to complete a transaction, to give a best effort. But the hardware will have the ability to say, I wasn't able to do it, and the system will fail over to a software implementation. And the challenge in that research, and this is not research that I did, is to have a running system where there are software transactions and hardware transactions happening at the same time.
But of course, from a developer's perspective, in some way you don't care, because as long as the language provides the features, I don't care whether the compiler delegates to the hardware or just does it himself.
You're absolutely right. And what you do care about is the semantics. When I say the atomic happens all at once, what do I mean by that? And there are some caveats that we haven't talked about yet, and these are caveats that the community is still working its way through. For example, the vast majority of systems do not let you do I/O while you're in a transaction, because how are you going to undo it? And there are some other things that if you assumed all the implementations are hardware, or you assumed all the implementations were software, you might have slightly different lists of caveats. And what we in the transactions community need to do and are working at is figuring out what those differences are and what we should be promising in our programming languages that, on the one hand, lets programmers not care, and on the other hand, allows a range of implementations. Hardware if you have it, software if you don't, and so on.
So from your last couple of paragraphs, basically, I derive that this is still a research topic. It's not something that's used in production, right? But I guess it's implemented in probably there is a JVM with transactional memory somewhere.
That's right. So let's see. It is still an active research topic. I don't know of a commercial, say, JVM that you can use right now with transactional memory. There are certainly publicly available research prototypes. On the other hand, all the major companies that write VMs, write big software systems, produce big chip numbers of multi-core chips are not only aware of the transactional memory research, but have research and development teams working on it. There's been published papers on transactional memory from research groups at let's say in alphabetical order, Intel, Microsoft, and Sun. So there's a lot of industrial interest, and I have no inside information and I have no crystal ball, but I would say we're talking a small number of years before some of these ideas are available.
So is there any relationship to optimistic concurrency and lock-free concurrent algorithms? That's something else we talked about in the episode with Brian and David quite at the end in the area of advanced stuff.
Yes, there's very much a connection. And here's how I like to explain it, and I hope the people who understand this connection better than me will like my explanation, is that transactional memory is an optimistic concurrent data structure. So just like you might have a queue that works with optimistic concurrency and has operations like NQ and DQ and things like that, transactional memory is just one that has operations like begin transaction, end transaction, abort transaction, read memory, and write memory.
Mm-hmm.
And once you have that, what's great is that the programmers can just, or the compiler or whatever, can just use those operations, and all the optimistic concurrency is under the hood. It's just in the implementation of the data structure, the same way that using an optimistic queue should not be any more difficult than using a traditional pessimistic or lock-based queue. And I have another analogy here that I really like, and hopefully you and your listeners will like too, which is that think about error correction. Mm-hmm. If all of our application programs had to deal with error correcting codes for memory, it would be a huge burden.
Yep.
But we get it for free because our memory does error correction for us.
Yep.
And so the idea with transactional memory is that we can get the optimistic concurrency sort of once and for all, and as long as we use the transactional memory system, we get the optimism without actually having to understand the clever algorithms that are used inside it.
Mm-hmm. Okay, so let's get to the meat of the matter, I guess, and talk about the analogy between garbage collection and transactional memory. So maybe I should briefly explain how you wrote the paper and then explain the challenge of doing that on the podcast.
Sure.
So what Dan actually did was he wrote a bunch of paragraphs on different aspects of garbage collection, and then basically took the wording of these paragraphs literally and exchanged a couple of nouns. The idea was to have basically take exactly the same text and just exchange a couple of nouns and verbs and take exactly the same structure to explain transactional memory and concurrency. And you advise that people should read this stuff twice, once to understand, and then the second time to see the correspondence between the two. And of course, we can't do that in the podcast. So we have to.
That's right.
The analogy might not show as nicely as in the paper when we discuss these things now.
Well, I'm certainly comfortable with the conversation throwing out some of the interesting ideas, and then of course you're right. It is the sort of thing that is best done from reading it. Although
right.
This idea of an analogy, just like you explained it, is for an analogy to make sense, I have to convince you that I'm saying true things about both. I'm
Sure.
saying things about garbage collection you agree with, and I'm saying things about transactional memory that you agree with. And then I have a third obligation, true things on one side, true things on the other side, which is that those things are so similar in structure that something deep is going on.
Yeah. So what we'll do now is we'll step through these different aspects you've been looking at, and we'll put, of course, the link to the paper into the show notes, so the people who want to look at at the document to see how this really plays out very nicely can actually read this stuff, of course. So let's look at the two problems and how they are similar.
Sure. So we've already, I think, talked about it on the transactional memory side, but we'll do both. So the problem with doing memory management, and you have to think back to programming in C or C++ without a garbage collector, and think about when you were really thinking about memory management, is that you're trying to use as little memory as possible because you don't want to run out of space or use so much space that your program is sluggish or consumes a lot of resources.
Yeah.
But if you use too little, your program will actually be wrong, right? So on the one hand, you have space leaks or space exhaustion. You're keeping around too much memory, and you have a performance problem. On the other hand, you have dangling pointer dereferences. If you deallocate memory before you're actually done with it, then your program is completely wrong.
Mm-hmm.
So you have to balance this correctness, keeping memory around as long as you need it, and performance, not keeping it around any longer. So that's the memory management side. And let's see if I can switch to the concurrency side.
Yeah.
And this is something we talked about before, but it's worth repeating
Sure.
right next to it if
Yeah.
you're going to do the analogy,
Yeah.
which is you're trying to have as much parallelism as possible, let multiple threads run at the same time, and if you don't have enough of that, you're not actually writing a parallel program. You end up having the performance problem of really only one thread running at a time, or if you're even worse than that, deadlocking and not having any threads running at all.
Mm-hmm.
So you want to try to keep as much parallelism as possible from a performance angle, but if you have too much, you end up with race conditions, multiple threads stomping on the same memory at the same time, and then your program is typically not correct. You end up reading two parts of a value that don't make sense together and things like that. So we have the same dilemma of if we do too much in this, on the performance side, we'll give up correctness, and if we work too hard for correctness, we'll end up giving away the very performance advantages we are trying to achieve by going for parallelism.
Mm-hmm. Yeah, and I think even in the way you talked about it now, the analogy shines through. Really cool. Let's go to the next aspect, which is the solution. In one case, garbage collection. In the other case, transactional memory.
When you go to solve either of these problems manually, you end up using pretty subtle protocols that all of the code in your application has to obey. So on the memory management side, maybe if you're doing it manually, you have an extra field in each object with a reference count, or whether it's still needed, or you tightly control what can point to what else so that you know when you're done with something. And when you implement a garbage collector, if you ever have, it turns out you do all those same things. You have subtle protocols. All of the memory in your system is laid out in a certain way. There'll be header fields. There'll be certain bits that are set to 1 if you're done with something and 0 if you're not. So all of these subtle whole program protocols are there, but they're not part of the program. They're now part of the runtime system where people who devote their lives to writing good garbage collectors and are real domain-specific experts in that can get it right exactly once. Mm-hmm. Now, they don't know anything about your application, which is the challenge. You know, anytime you try to have a one-size-fits-all solution, it's not going to be specially tuned to the application, but they know how to write garbage collectors. And so then for transactional memory, it's the same idea, that now what we want to do is we want to somehow keep track of, are these two transactions accessing the same memory? And the other thing transactions have to do is they have to have some way to take multiple updates to memory and export them all at the same time. And the protocols in doing that are extremely subtle and involve all of the code in the application doing the same thing and doing it correctly. But again, we have experts, people who have developed these algorithms and can implement them once and for all and get them right.
Mm-hmm. Okay. And also, both cases aren't useful in every scenario. They are incomplete solutions in some sense, right?
Yeah. And, you know, I think garbage collection is great, and I don't want to come across as saying anything otherwise, and the same for transactional memory. But certainly once you understand the approximations that these systems make, you can understand that I can certainly write programs where they do very, very poorly. So in garbage collection, remember, this key approximation is reachable. Whatever is still reachable will stay live. And anytime that's a bad match for what should stay live, anytime you have an application where a bunch of live things, reachable things, are no longer needed, programmers should really get involved and somehow make those things not reachable, either by using special language features like weak pointers, or simply going in and adjusting their data structures quite manually to make things no longer reachable. And when you start going down that path, you realize that you're reintroducing the problems of manual memory management.
Yes.
Suddenly the programmer has to get that just right, and they have to adjust their data structure to make things not reachable, not too soon, or they'll be incorrect, and not too late, or the data will stay around.
Yep.
And I have a little example in the paper, in fact, that says if you were a very, very stubborn Java programmer who really wanted to do manual memory management, you can do it. You can set up arrays of objects, and when you're done with an object, put it back in the array, and things like that, and you really regain all of the difficulties of manual memory management.
Yeah, and that's something that you might actually want to do in embedded or real-time systems, where it's important that the amount of memory is it's constant and is also known in advance when the system is built or deployed.
That's absolutely right. And I've even seen situations, and people who write garbage collectors don't like when programmers do this, but I've certainly seen programs where for certain very performance-critical classes and algorithms, people will do things like have an array of packet objects
Sure.
and simply cycle through it reusing the same packet object memory rather than constantly creating new packet objects and freeing them and going around the loop. And it really depends on your system and your garbage collector. People often have the intuition that that improves performance. It really depends on the system. They're often not correct, but it depends.
Okay. TM side?
So on the transactional memory side, we have an approximation that is the analogy of this reachability approximation, and that is that we don't let two transactions proceed in parallel if they have a memory conflict. And that almost means access the same memory. It turns out that as long as they're both just reading the same memory, we typically allow parallelism in that case. But if there's a read-write or write-write conflict, we will not allow them to both proceed. And there are situations where that is unnecessarily conservative. For example, if they are both just incrementing some counter that's just used to, say, generate unique identifiers, it doesn't really matter that they conflict. One of them writes 2 to the counter, the next one writes 3, the next one writes 4. It doesn't really matter. But from the system's perspective, from the implementer of the transactional memory, it doesn't know that. It sees that because of this conflict, one thread saw the value 3 when it should have gotten the value 2. And in some sense, only the application can know that it doesn't matter whether it saw 2 or 3. It just has to be a unique value.
Mm-hmm.
And then I go ahead and show that the extreme case, just like a Java programmer can regain the pluses and minuses of manual memory management, someone programming with transactional memory can write a lock class, can go ahead and implement locks on top of transactional memory, and then choose to program in terms of method calls like acquire lock and release lock. And then they'll have the same race conditions and deadlock potentials in their application that they had before.
Mm-hmm. Very nice. So I think these three aspects, the problem, solutions, and the incompleteness of the solution, is probably, well, from my perspective, it's the core of the analogy. But it goes even further, I guess.
And you're absolutely right that is the core of the analogy. But then some of the details turn out to push the idea further. So in garbage collection, it turns out the two very basic approaches are tracing, which subsumes copying and mark sweep, and reference counting. And it turns out in OOPSLA a few years ago, there was a very nice paper relating these two basic approaches and showing that they're actually duals, kind of complete opposites of each other. Mm-hmm. In some sense, tracing traces the live data, and reference counting traces the dead data. And that's a much harder thing to see, and I'll have to point you to that work. I think it was 2005 in the OOPSLA conference.
We'll find out.
Yep, that's right. 2004. I'm sorry, 2004. Mm-hmm. A paper, A Unified Theory of Garbage Collection. On the transactional memory side, now we have to get into just at the very highest level how transactional memory is implemented. And again, there's two basic approaches. One is that a transaction, while it's running, goes ahead and updates memory, but then if it can't complete because there's some conflict with another transaction, it undoes or rolls back everything that it had done previously. Mm-hmm. The other possibility is to not update shared memory, but instead while a transaction is running, it works on a private copy. And then if it successfully completes, then it reflects all the changes back to shared memory using a complicated protocol to do that. And the interesting thing how these two are opposites is that if you do the update in place, the first version I talked about, then committing a transaction is trivial and aborting it is rather difficult. Yeah. And if you do it with the private memory, it's the exact opposite. Aborting it is trivial and committing it is quite difficult.
Mm-hmm. And difficult also in the sense of performance cost.
That's right. In both cases, the cost is usually of the difficult part is proportional to the number of memory locations that you wrote to. Yep. Which is good news and bad news. That can sound big, but remember, of course, you already took the time in your application to write to them. Yeah. So it's at least a proportional cost. Yeah.
Okay, you already mentioned before that I/O is a problem in case of transactional memory because you can't undo I/O. So how is that in both cases?
Well, maybe I'll just remind listeners that I/O and garbage collection is also difficult. This is why we serialize objects rather than actually writing out the pointers to disk. Because if you write out a pointer to disk and the garbage collector doesn't know you've done that, it might think the object is no longer reachable, collect the object, and then if you read the address back in, you might think that you can still access the object. And this is why languages like Java don't let you actually write addresses out to disk. This is also a challenge in distributed computing. Distributed garbage collection is a well-studied topic that, again, is much more difficult than in the non-distributed setting. And so here in the analogy, I guess the biggest thing is the first question people are often asked about transactional memory is, well, what about I/O? It'll never work with I/O. And I am optimistic that just like we've learned how to sort of restrict programs enough that garbage collection works even in the presence of I/O, hopefully we can do the same thing for transactional memory.
Yep. Fault sharing, progress guarantees, and static analysis improvements. How do they fit together?
The performance of both garbage collection and transactional memory is not completely under programmer control. You can get a long way if you really know how garbage collectors work and you program in certain ways. You can really program against the garbage collector to get certain performance benefits. But there are situations where you just cannot. If your memory allocator, which is in some sense part of your garbage collector, chooses to put two objects on the same cache line, can really hurt your performance, and this is not something under programmer control. And it hurts you both in the memory management standpoint. Things might live longer than you expect, and hurt you in the transactional memory standpoint. Sometimes there's false conflicts. There's transactions abort even though you didn't access the same memory. Maybe you're accessing different fields of the same object, but the particular transactional memory system only detected things at the object level. And so there's an open question in the transactions community of how much we need to expose this to programmers. So that's an example of how things are not under your control. Static analysis optimizations, certainly programmers can't control exactly what compiler optimizations are used, and that can really affect how long memory lives and can affect how often transactions abort and things like that.
We recently had an episode, well, by the time we published this one, it's not recently anymore, about static analysis tools, and there, of course, they have the challenge of trying to understand what the program does, because a lot of the semantics is hidden in complex protocols, especially in concurrent systems. So making things more declarative, which is what transactional memory does, of course makes static analysis and therefore error detection as well as improve performance enhancements or performance optimizations, makes it much more feasible.
Right.
So, well, the essence of concurrency, as you say in your paper, is basically trading efficiency for engineering effectiveness, right? So you want to make life easier for developers by providing transactional memory, but they might have, well, the program might not be as good or as fast as if it was a nicely handcrafted and correct log-based system. So how much more easy is concurrency going to be once we have transactional memory? What are the advantages for developers?
So I'll answer that question 1 second. This is certainly my perspective, but I should be fair to the community and say some people point out that transactional memory can actually be faster because there's optimistic concurrency, and that programmers are not particularly good at handcrafted lock-based solutions that are particularly efficient.
That was I was trying to hint at by saying a well handcrafted and correct. And people probably typically don't do this.
It's not clear that lock-based programs, even carefully crafted ones, will beat transactional memory. Transactional memory may win, but I agree with you that even if transactional memory gives back some of the straight-line performance, the ability to write robust parallel software in an easier way is worth it. And I think the biggest reason, if I can pick just one, is that it's easier you don't have to maintain a locking protocol. You don't have to keep track of what lock am I going to acquire before I access this field. In some sense, that is done for you automatically. And in particular, for avoiding deadlock, it's very hard to write an application if you ever need to hold more than one lock at once. For example, if you need to transfer some data from one object to another, and you need to acquire both locks, Well, if some other thread requires the same two locks in the reverse order, you can deadlock. And it's very hard to choose an order.
Mm-hmm. So, just as a remark, the idea of trading efficiency for developer effectiveness in transactional memory is, of course, the same thing for garbage collection. You make things easier for developers, but it might not be as optimized as if memory was managed by hand correctly. So there is another analogy.
Right. Exactly, absolutely, and the analogy goes further as well, that there are situations where using garbage collection will be faster than not using garbage collection.
Yeah,
the standard reason is that when you collect data and you move objects around, you can get them to fit in cache, you can get them to fit on the same cache lines, things like that. You increase locality.
Mm-hmm. Exactly.
Yep.
So, will concurrent programming be as easy as sequential programming with transactional memory?
So this is the key question that I bring up, is just because this analogy is there doesn't mean that we'll introduce transactional memory and suddenly parallel programming will be as easy as sequential programming with garbage collection. Not at all. Everything about transactional memory is about from a programmer reliability standpoint. Maybe I shouldn't say everything, but a big part of it is letting you just write atomic left curly brace statement, right curly brace, instead of having to choose a particular lock and worrying about race conditions and deadlocks. Mm-hmm. But what it doesn't talk about is where should you put that atomic statement.
Right.
It's still the programmer's job to decide what is a transaction, what collection of operations need to happen all at once.
Yeah.
And there's still the trade-off. If you make them too big, you'll hurt performance. If you make them too small, you'll hurt correctness.
Yep.
And the analogy doesn't help with that.
Mm-hmm. Mm-hmm.
And it's exactly what does not come up in sequential programming. In sequential programming, there's no idea of what group of events need to happen all at once before another thread sees them, because you're the only thread.
Mm-hmm. Yeah, sure.
So at some point, sequential programming is a special case of parallel programming, and so there's not going to be an analogy that that's going to reduce the general case to the special case. It just doesn't exist.
Yeah. Okay, so here is the $1 million question. What's the point of the analogy? Why did you write the paper?
Why did I write the paper? For a couple reasons. One is that I think it will really help with research. Okay, that once you have an analogy, it can motivate new ideas. Mm-hmm. Right? I look on the garbage collection side, and I see generational garbage collection, an idea from the early to mid '80s that has been extremely important in efficient garbage collection implementation techniques. And I don't yet see something on the transactional memory side. And if writing this paper can inspire someone to come up with something just as important on transactional memory by thinking, what is the thing on the other side, I think that would be a huge advance. Mm-hmm. And so this idea of using an analogy, even an informal one, to come up with new ideas is something I think humans do all the time. And I wanted to share this one so that other people could come up with ideas. Less important reasons are I think it can help explain transactional memory.
Absolutely.
Just to understand what it is. It's a new thing. A lot of people know about garbage collection. Maybe this will help them understand some of the limitations and benefits of transactional memory.
It worked for me.
And the final reason I have to admit is once I saw all these connections, I just thought this was, one of the most beautiful things I've ever seen in computer science, and I wanted to share it.
Yeah, absolutely. And again, I recommend listeners to become readers and read the paper. From the analogy, you also risked a couple of possible predictions about hardware support and other stuff, right?
Right. So I have a section in the paper. We've talked really about the technical stuff, coding and software engineering, and really the theory of garbage collection and transactional memory. But then I said, there's some other things we can say about garbage collection that might or might not be true about transactional memory. One is, a lot of time, if you go back a couple decades or 3 or 4 decades, people felt that garbage collection was very slow and absolutely needed hardware support. The old Lisp machine had hardware support for garbage collection. And people don't feel that way anymore. And so perhaps if we push the analogy a little too far, people will someday feel that transactional memory doesn't need hardware support either. I just kind of throw that out almost to be provocative. Mm-hmm. The second one is that, we had the basic garbage collection algorithms figured out in the 1960s. And I say we in the general sense. I
Sure.
wasn't even born yet. And yet, garbage collection in the mainstream, we're really talking the 1990s. And so, unfortunately, we may need to be prepared for transactional memory to take a slower road to mainstream adoption than many of us would like.
Mm-hmm. Sad message, but probably realistic.
Yeah. But, I'm actually, even though I say that in the paper, I'm actually optimistic. There's all the new high-performance computing languages, Chapel from Cray, X10 from IBM, and Fortress from Sun. All three of them have an idea of transactions and atomic statements in their draft languages. Yep. And so, should those languages take off, and I think they're all very interesting, I think transactions will get out pretty quickly.
Mm-hmm. Yeah. So playing devil's advocate, and now not with regards to your analogy, but rather to transactional memory in general, isn't it a trivial finding that making something that developers had to implement as procedural statements, protocols, making that part of the language and making that more declarative, isn't it trivial to find out that this is an advantage?
Yeah, on that level, absolutely. Moving things higher level, providing runtime services, all of those things. In that sense, it's not, the analogy is so basic, so simple. It's just that one idea that we could throw a lot of things in. Exceptions, getting rid of GoTo, library support for serialization and process migration. All of these things, just give something to programmers that they used to have to do in a tedious and error-prone way. Yep. And I think what goes further here is the idea that memory management is about reusing memory as much as you can, but not more. And concurrency is about getting as much to happen in parallel as you can, but not more. And that this, in some sense, it's time versus space. Memory management is about space. Parallelism is about time. And garbage collection and transactional memory as solutions are rather similar runtime services, much more similar than I think has been appreciated before. And could you take a third thing, like one of the things I mentioned, like exceptions, and try to write, 4 or 5 pages of sentence-by-sentence analogy with garbage collection? Maybe, and if so, I'd love to read it, but I don't think so.
Yeah. So the remaining challenge you mentioned is, of course, the transaction demarcation, too big, too small, and so on. How much can we learn from the database community? How much interaction is there between the transactional memory community and the database folks?
Well, there's this old joke in programming languages that what we do is we take database solutions from 20 years ago and finally figure out what they were talking about. And there's some truth to that. I feel that myself and perhaps some of my colleagues in transactions have not learned as much or learned as quickly from the database community as we should. But there are some important differences as well. In the database world, the data is much more structured. And the programming languages, if you will, things like SQL and things like that, are much more restrictive on purpose, and that makes sense in that domain. In our general purpose programming languages, perhaps we should not let you start and end transactions wherever you want. Or we should provide some sort of tool support for helping you to determine what invariants are maintained depending where you start and end your transactions. Maybe there are things to learn from the database community about where transactions should begin and end, but I do think it's a harder problem for us. I think in the database world, and maybe I'm missing something, it's usually easy to say, well, this update to the personnel records, just needs to be a transaction, or this money transfer needs to be a transaction. And in our more general purpose, unstructured applications, I'm not sure programmers are as good at drawing those lines.
Okay, to wrap this up, concurrency is obviously becoming more and more important, and transactional memory is a hot topic there. What other approaches are there on the horizon that might make concurrency more tractable for Joe developer, as we say. For example, one thing we talked about was the message passing stuff in Erlang, or for example, also Scala's actor framework or something. So what do you see? So will transactional memory, is that the only kid on the block to make things easier, or are there alternatives also in the shared memory space?
Well, I think it's certainly the biggest kid on the block if you look at research interest and that sort of stuff. And I think you've drawn exactly the right distinction, that I think in the space of shared memory, it's, in my opinion, the biggest and most intriguing advance we've seen in a while. Now, the basic idea for transactional memory actually goes back to Elliott Moss and Morris Herlihy in the mid-'80s. So, a lot of this is fleshing out the ideas and extending the ideas, being more efficient. All the software stuff came later, and so on. But transactional memory is big in the shared memory space. But whenever I talk about transactions, I always say, but that's just in the shared memory space. Mm-hmm. I think there's a huge space. Erlang, for example, not just has all this message passing stuff, but one of the reasons it works so well is that it's a mostly functional language.
Yep.
And the great thing about functional languages is if you don't mutate memory, your synchronization problems go away to a large extent. Yep. The first thing when I teach sophomores concurrent programming, which may surprise some of your listeners that we do now, and I think this will become more common, teach sophomores basics of concurrent programming. Yep. The first thing I tell them is don't use concurrent programming unless you have to. Yeah. Second thing I tell them is don't share data unless you have to. Yeah. The third thing I tell them is if you do have to share data, don't mutate it unless you have to. Yeah. And only when none of that is appropriate for your application do we need to start talking about locks and transactions and memory updates.
But of course, for all these things, you need language support. Otherwise, you accidentally modify stuff and then you're screwed.
That's right. And I think there's a real opportunity here to revisit a lot of the classic ideas on programming models, language support for concurrency, message passing, coordination, things like that, and see which of them are going to help us. And I think I'm always of the opinion that it's not about finding the best overall solution and declaring it the winner. It's going to depend on the application and the language and the type of programmers. And it's a really exciting time for concurrency. You can be a cynic and say there's no new ideas, or you can be an optimist and say there's a new opportunity to extend and adapt those ideas to concurrent programming because it's so much more important than it's ever been.
Yep. Okay, so that was really, really cool. Very interesting. Is there anything I should have asked you but didn't?
Maybe I'd just emphasize again, this analogy is really all about perspective and about taking a big step back. And but the actual research that's making transactional memory happen has been done by a lot of really, really great people, a lot of colleagues of mine. And if this analogy can kind of serve to help popularize or make available some of their work, then that's another advantage of it. This was an insight and an essay that's sort of really me having the chance to take a step back, and it was really fun to do and fun to talk about with you, and I'll have fun talking about it at OOPSLA. Yep. But we've got a lot more down and dirty work to do too, and we're doing that as well.
Okay, Dan, thank you very much for being on the show.
You're welcome.
Thanks for listening to Software Engineering Radio. If you want to get more information about Software Engineering Radio, or if you want to give us feedback, please go to our website at se-radio.net. You can also contact the team at se-radio.net, although we prefer entries in our comments system on the website so other people can see what you think. Software Engineering Radio wants to thank Henning Pauli for the intro and outro music, as well as Libsyn for providing the bandwidth. This episode of SE Radio, as well as all other episodes, is licensed under Creative Commons license. See the Software Engineering Radio website for details.